All right, we're going to do one more short video, make up a little bit for the fact that you have a quiz today and we got Labor Day coming up. So we're at the point where we were talking about the ways that we measure water vapor in the atmosphere. And so we're going to press forward on this now and see where we end up in the next 5-10 minutes. Measuring water vapor, one of the big things that we utilize is vapor pressure. We've talked about pressure, force per unit area, and how much pressure is ultimately being exerted by water vapor in the air. This is pretty simple, folks. It's actually just to where high vapor pressure simply means there's a lot of water vapor. This means it's an absolute measure of how much moisture is in the air. We'll talk about other ways in which we measure it in a relative sense, but when we're actually comparing something directly to how much water vapor is in the air, we call that an absolute reading. We express vapor pressure in millibars. Not surprising, as this is how we also measure atmospheric moisture. So one of the questions we ask is how much water vapor can air actually hold? And this ends up being a very important concept. The fact is that it depends primarily on the temperature. Again, you feel muggy if there's a good amount of moisture in the air and it's warm outside, but you can be saturated outside on a cold day and you simply don't feel like it's that muggy. And this is the fact that warm air can hold more moisture than cold air. Again, hot days have the capacity to hold more moisture than a cold day. And so we need to introduce the concept of saturation vapor pressure. Remembering what saturation means, here we're looking at the actual maximum amount of vapor that can be held at a given temperature. In other words, how much vapor is needed to make the atmosphere, or any object for that matter, saturated at a given temperature. And so when we take this idea of warm air having the capacity to hold more water vapor, it simply means that it has a higher saturation vapor pressure. It means that on a, say, 85 degree Fahrenheit day, we could hold maybe 30, 35, 40 grams per kilogram of water. On a cold day, we can hold a fraction of that. It's actually an exponential relationship, as we'll see shortly. But you don't feel muggy even when it's completely saturated in the dead of winter, because cold air cannot hold much moisture. And so this will be something that comes up on labs moving forward, and something that admittedly is going to take a little bit of time to grasp. So you may want to rewatch this, and we'll probably revisit this within the lecture environment sometime next week. And so what you have here is the saturation vapor pressure curve. And on this curve, this red line on the graphic, it basically shows what is the saturation vapor pressure. Again, looking at your y-axis, we're looking at that vapor pressure in millibars. And so you can see at temperatures negative 30, none. By the time we get up to 0, maybe about 6. By the time we're up to 20, now we're getting close to 25. And as mentioned earlier, when we're up at 30 degrees Celsius or mid-80s, you can hold a little upwards of 40 millibars for your saturation vapor pressure. This is again an exponential relationship. You can quickly have more moisture in the air as temperatures rise. Ultimately, as we'll talk about shortly, you can have actual vapor pressure anywhere along or below this curve. If we were to be above the curve, that would simply say that we were supersaturated, and we're not going to worry about that for the purposes of this class. And so again, keeping in mind this exponential relationship is why when temperatures are warm outside, we can potentially not even be saturated. Maybe we have an actual vapor pressure of 30 millibars when the saturation vapor pressure is 42. But if we had full saturation at a temperature of 50 Fahrenheit, it would still have 1/3 of the amount of moisture in the example that I just described. And so here again, you can see at 10 degrees Celsius, the saturation vapor pressure is 12 millibars, but at 30, a simple 20 degrees Celsius increase, you've already increased up to 42 millibars. Warmer air, therefore, has the capacity to hold more moisture, and we need more vapor pressure, more actual water vapor to make it saturated at warmer temperatures. In reality, in areas across the United States, as we get up into the mid-80s, the low 90s, or even up into the hundreds, we don't reach saturation. It will still feel incredibly muggy on some days, but very rarely do we find another measure of water vapor, dew points, reaching values that high. And so this is, again, I mentioned this earlier as I kind of sketched it out with a mouse pointer. Actual vapor pressure can be anywhere on or below the red curve for this graph. And so again, maybe it's a cool fall day and it's raining. We may be saturated and be right on that red line. A muggy day watching the ball game, you may have a saturation vapor pressure that's not on the red line but still makes it feel muggy outside. Or you may have a day that it's snowing but doesn't feel muggy at all and it's still saturated outside. The inset talks about the difference between the saturation vapor pressure with respect to water or liquid and the saturation vapor pressure with respect to a solid or ice. We'll explore this more on an upcoming lab. Another measure to tell how much moisture is in the air is relative humidity. And in fairness, if there's one parameter or one way of explaining the amount of moisture in the air that you're probably familiar with, this would be it, relative humidity. I doubt many of you have heard of vapor pressure, but this is what they would show on the news. Relative humidity is actually a ratio. It's a ratio between the actual amount of water vapor and the amount of vapor required for saturation. And so we talk about relative humidity after vapor pressure because of the equation expressed in the box. Actual vapor pressure, or the actual amount of moisture in the air, divided by the saturation vapor pressure, or how much vapor pressure the air can hold at a given temperature, and we usually multiply that by 100 to express it as a percentage. So the question is relative humidity a good measure of atmospheric moisture? Knee-jerk reaction is, sure it is, because this is what they often talk about on the news, or is a way that we're at least familiar with. In reality, actually, let's take a step two. We have a second question. How do we change the relative humidity of the air? And there's two ways in which we can do it. Actually, let's take a step back. So question one, let's actually go ahead and answer it now. Relative humidity, is it a good measure? No. We can have a relative humidity of 100%, and if it's cold outside, it doesn't really tell us a lot about whether or not we would feel like the air is saturated or heavy and kind of ugh. But if you have a relative humidity of 60%, but the temperature is in the mid-90s Fahrenheit, it's going to feel oppressive outside. And so relative humidity is relative to the temperature. That's how you can remember how relative humidity is expressed. And so let's move on to question two. How can we change the relative humidity of the air? Thinking about the numerator, actual vapor pressure, and the denominator, the saturation vapor pressure. So first we can change the relative humidity by changing the numerator. How much actual water vapor exists in the air? In the schematic here, top couple lines, you can see that the air temperature remains constant at 20 degrees Celsius, but by adding water vapor in the second version, we increase the relative humidity. In other words, the saturation vapor pressure, or the denominator, remains constant, but we've increased the numerator and therefore we make our relative humidity larger. The other way to change relative humidity is to simply change the temperature of the air while leaving the amount of vapor constant. In this example, we increase the temperature from 20 degrees Celsius to 30 degrees Celsius while not changing the amount of vapor. This means that the numerator remains the same. The denominator, or the saturation vapor pressure, which is that exponential curve, increases sharply. And so in this example, by raising the temperature but keeping the amount of vapor steady, we make for a smaller relative humidity. Give this slide a couple moments and think about it, how we could potentially change it in the opposite directions as to what is shown here in the schematic. So when we consider relative humidity with relation to temperature, nighttime hours, our diurnal curve, usually getting coolest around 6 a.m., that may be though when our relative humidity is the highest. This curve is assuming no drastic changes in the amount of water vapor. And so if we have continual water vapor but cooler temperatures, our saturation vapor pressure decreases, and therefore our relative humidity increases. The opposite is true in the afternoon. As our temperature gets higher and higher, the air has a capacity to hold more moisture, but if we don't actually increase the amount of moisture in the air, the relative humidity decreases into the afternoon hours. This is pretty common, and we'll take a look at some examples in real time in class. Another way to measure water vapor that you may have heard of is the dew point. The dew point is simply the temperature to which air would have to be cooled in order to reach saturation. And so yes, this is going to be oftentimes noted in the fact that you find dew on the grass in the morning hours. The dew point is always going to be the same or less than the air temperature. In other words, if the air temperature is 30 degrees Celsius, your dew point is going to be 30 degrees Celsius or lower. You will not find a dew point higher than you will the temperature. As the dew point gets closer and closer to the temperature, your relative humidity increases, your vapor pressure increases, and you get closer and closer to the saturation vapor pressure. And so if you start to think of these different ways of measuring moisture in conjunction with one another, as your vapor pressure and saturation vapor pressure become the same, your relative humidity increases to 100%, and your temperature and dew point become equalized. Again, one small caveat, we don't get into great detail about this, but to be perfectly clear, dew point is the temperature to which air would have to be cooled to reach saturation, assuming no changes in pressure or moisture. We could make changes to these values and get us closer to saturation, as we've seen on some prior schematics. If you note in the bottom corner, I will have the slides available soon, you can click here to look at the mixing ratio. The mixing ratio is a measure of moisture that we do not spend time on at this point, but is an interesting way of looking at how much moisture, again, is in the air. And so we'll conclude with a couple of quick slides here with regard to dew points. Here we're looking in January. You can note the dew points in this part of the country, somewhere between 10 and 20, and again, these are in degrees Fahrenheit. And so these are going to be when the temperature outside is probably about 30. And so our dew points are again going to be lower than our temperature. You can note we have higher dew points across Florida and portions of the West Coast, and lower dew points as we move up to the northern plains in Canada. As we work our way into July, you can notice a surge of dew points across areas east of the Rockies. Dew points across this part of the country in the 60s to near 70 are usually going to be indicative of increasingly muggy conditions. 65 is typically the threshold, and again, I'm using the unit of Fahrenheit, when people start to feel somewhat uncomfortable. 70 to 75 is when it starts to feel a little oppressive outside in terms of dew point. Again, it's all relative. A dew point of 70 plus in Miami would be considered a typical day, whereas if you saw dew points approaching 70 degrees in Denver, Colorado, there would be a high likelihood of severe weather. Notice that we get much lower dew points west of the Rockies. This, as we'll see in some upcoming lessons, is because the primary source of warm, moist air in the United States is the Gulf of Mexico, and the Rockies serve as a very effective barrier for that type of moisture to make it west. All right, I promised I would keep this relatively short. That's the only other video for today. We will see you all on Monday.